Professor Derek Kimball. Actually, so we've known each other for a while, right?
Like yeah.
5, 10 years, something like that.
Go back. It's a blur now.
Anyway, so basically he uses techniques from experimental atomic physics and nonlinear optics to do precision tests on fundamental laws of physics. So he was the first one to establish an externally funded physics research program at Cal State East Bay, which is where he's at. He's mentored over 60 students. Yikes. That's amazing, right? In his research laboratory. More than 20 of his students have gone on to graduate physics programs, and 3 of his students have been awarded a National Science Foundation Graduate Research Fellowship. Nice. Okay, former students now have careers at Intel, Google, Tesla, Lawrence Berkeley, Lawrence Livermore National Labs, and so he received his PhD in 2005 from University of California at Berkeley under the mentorship of Professor Dimitri Budker, who's actually a very well-known name in this field. So he studied nonlinear magneto-optical rotations and its application to precision measurements of atomic spin precession. He's actually co-authored a book, Atomic Physics and Exploration Through Problems and Solutions. It's with Oxford University Press. And another one, Optical Magnetometry, with Cambridge University Press. And he has over 70 peer-reviewed research articles. So for all his good efforts, he was punished by serving his chair at Cal State East Bay from 2011 to 2014, and also during 2016. And so he's 2021 chair of the American Physical Society's topical group on precision measurements and fundamental. Oh, you're chair of that?
I was.
Oh,
and now I'm retired. So
okay.
I just had 1 year here.
So he was named Cal State East Bay's 2011-2012 George and Miriam Phillips Outstanding Professor, and in 2019 received a Spitzer Distinguished Science Faculty Award. And the last but not least, in 2018, Professor Kimball was elected a Fellow of the American Physical Society. So I mean, I don't know if this is like in England, you'd be knighted, right? So it's like the scientific sort of equivalent. Like, so being a Fellow of the American Physical Society is like a big deal. Okay, anyway, after that much too long introduction, let's welcome Professor Kimball. Derek.
Wow. Thank you so much, Doug, for the invitation to come speak, and that was a really, really kind, very kind introduction, and we're very grateful for that. But I'm really, really excited to be here. And I was, of course, last night when I was planning on driving down, I was like, oh man, I'm going to make it. Should I bring a canoe with me too, just in case? But it was fine. It was fine. So I'm super glad to be here. It's super fun. So. Yeah, to begin with, so Cal State East Bay is a fellow of Cal State, and we don't have a master's program actually at Cal State East Bay. So all of our work is done by undergraduates, and so first and foremost, it's been a great experience getting a chance to work with all of these undergraduates over the years and kind of give them their first taste of experimental physics in the laboratory and the epic highs and lows of trying to pull off an experiment. And that's one of the reasons I wanted to become a professor at a Cal State, especially with a focus on undergraduate education, is because I remember, so actually Dimitri Budker took me into his group when I was an undergraduate, and I had my first taste of things exploding in the laboratory and not working, and then finally working after a long time, with just the thrill of the whole experience. And to get that, share that with other people, I mean, it's the biggest honor, one of the biggest honors of my life. So I want to thank all the students. They're just amazing, and I have made a collage of some of the students, that we've worked through throughout the years that have gone on to great things. So anyways, a lot of great gratitude for all the wonderful students. Okay, so I'll give you a little outline. Oh, and first and foremost, I should say as well that totally informal talk. So if I'm talking and something you see on a slider that I say inspires a question or a comment, feel free to raise your hand, interrupt, and I'm easily distracted. We can go off topic for a little bit and talk about something else. But if I don't get too distracted, this was my plan. So I'll give a little overview. I don't know how many dark matter talks you have to listen to, but if you haven't had too many, I'll give you a little quick overview of why we think, what dark matter is and why we think it exists. And then, so in our experiments that we're focused on right now, we're testing one of the hypotheses about what dark matter might be. And that hypothesis is this made up of these ultralight bosons. And by ultralight, we mean they have really, really tiny masses, right? So if you look at like standard model particles, right? So you think of like the neutrinos have a non-zero mass, but it's very, very tiny. It's the lowest massed particle in the standard model that has a non-zero mass. And we don't exactly know what its mass is, but we can say, you know, from the neutrino mixing, it's like on the order of fractions of an electron volt, something like this. But the particles we're talking about here are like 10 to the minus 9 electron volts, or 10 to the minus 12 electron volts, or 10 to the minus 15 electron volts. So like orders and orders of magnitudes smaller masses than the neutrinos, which is a whole weird regime to be in for particles. So there's some somewhat non-intuitive like things that we're not used to about them from other particles we're familiar with that we can talk about. So then I'll talk about our 3 experiments, and just for fun, because it's the one that's like has the latest, most recent breaking news results. I started with the search for non-interacting particles experimental hunt, the SNIPE Hunt, so I'll tell you about that. And we have another experiment that we work on so all of these, actually all these experiments too I'm doing in collaboration with other folks. So the SNIPE Hunt actually is a collaboration with other undergraduate institutions, so that's kind of cool. And then the CASPEr, the Cosmic Axion-Spin Precession experiment, actually is a collaboration with my former advisor, Dmitry Bucher, that raised me, so we're still working together. And actually another friend from graduate school that was also a DEMA student, so that's the collaboration there. And then we have this global network of optical magnetometers for exotic physics searches, or GNOME, which is a collaboration of a bunch of folks all over the world, a lot of them friends from grad school and people I met and things together. So, you know, I guess another little secret is that, you know, in certain, you know, one thing I think, especially coming out of the pandemic and everything that you learn to appreciate is that, you know, physics is, you know, it's not just some objective, you know, search for truth and everything. It's also like a community, you know, effort, right? There's a big social component of it, like, you know, having relationships with people and discussing ideas and trusting each other and getting into debates and all this stuff. And that kind of vibrant community aspect of physics is like the core of what we're doing. So in a certain sense, you know, a lot of these projects are just a great way to get a bunch of buddies together to work on fun questions and talk about cool ideas. So that's motivation enough to do some of this work. Okay, so let's start with the question of why we think there's dark matter. So maybe you've seen a pie graph like this before somewhere. So this is according to our best understanding of all the data we have so far, kind of compiled together what the universe is made of, right? So this is the energy density content of the universe. And so about 68% of the universe, as far as we can tell, is in the form of this dark energy that's responsible for the accelerating expansion of the universe. So it turns out that the universe, instead of you know, seeming to collapse in or just coasting, is being pushed apart by something. And that's this dark energy. What is it? We have no idea. It's invisible, so it doesn't interact with light, but other than that, we're pretty clueless. Now, 27% of the mass energy of the universe is in the form of dark matter, or at least that's the working hypothesis, also some invisible substance, but it's different. So it's matter-like, meaning that it has kind of this similar properties in terms of like the cosmology and things like that as other matter particles that we know of. So, and we know about it from its gravitational effects. But it has gravitational effects that other matter particles have. It kind of tracks together, right? And then only 5% of the energy content of the universe is ordinary matter, like hydrogen, helium, you know, all the gas of atoms that make up stars and other kind of interplanetary dust and things like this. So, you know, and I always like to say this is why, you know, when you get physics exams, I mean, you got to curve it, because I mean, if you ask physicists like, what's the universe made of, we get 5%. But you know, we still give ourselves like at least a B+, right, on our work. So, you know, so you got to take it with a grain of salt here. All right. So one of the original evidences for dark matter came out of the work of Fritz Zwicky. And so he noticed that galaxies in these clusters were moving too fast, in the sense that they are moving so fast that if you estimate from the brightness of these galaxies in the clusters how much mass is in those galaxies, kind of from the known relationship between light and mass that you can see in the local region, that they're going so fast that they shouldn't be gravitationally bound to each other, right? They just, you know, it's like if you were going down a hill really, really fast and you had enough speed that you just fly right off the other side and never come back again, right? That's what all the galaxies and clusters look like. But nonetheless, they seem to be bound to one another. So he was like, his explanation for this was some dark, invisible matter that was holding, the gravitationally holding these galaxies together in clusters. And then following up on that was really groundbreaking work by one of the great astrophysicists of our time, Vera Rubin, who showed that in fact, not only in galactic clusters did you see this. So Fritz Zwicky's work was kind of like interesting, but they kind of put it by the side. But then she showed in survey after survey after survey of the stars on the outer edges of the galaxies, of the visible galaxies, and of many different galaxies, and also the gas at the edges of these visible galaxies, it was rotating around too fast. Like if you take a rock and you attach a string to it and you swing it around your head, right? If you swing it too fast, right, then the string tension might not be enough to provide that centripetal acceleration of the rock around the edge, and then the string will break, right? And in the case of galaxies, that force is being applied by gravity, right? But if it's going too fast, the gravity's not enough to hold it in, it should just fly off. So you're basically in the same situation as they were, as Fritz Zwicky noticed with the galactic clusters. So you know, she's so famous, she made it on my T-shirt, so that's pretty cool. So here's Vera Rubin's work, and so the difference between what's predicted, right, from what you can see, the visible matter, right? So this is the galactic rotation curve that would be expected from visible matter, and that's the dashed line. Oh, I have a pointer here. So this dashed line here is what you'd expect, right, as you move. So this is the galaxy, and it's going to move further and further away to the edges, where really, you know, now you just have a few stars out at the edge, and gas and so forth. But what they observe actually is this curve, and with the uncertainties, and you can see the disagreement between what you'd expect and what's observed is huge. And it's not just one galaxy, it's all the galaxies. They all show this, more or less. Right? So to kind of visualize this, you can see, so without dark matter, you'd see that the stars near the center of the galaxy, closer to the center of the galaxy, would go faster, and the stars near the edge of the galaxy should go slower if they're gravitationally bound. But instead what you see, they're all going kind of like the same speed, like spokes on a wheel. Right? And this is kind of the dynamics of all these galaxies. And so, so again, the explanation is, you know what must be happening is there's some other matter that we can't see that's not absorbing light. It's neither absorbing light nor emitting light. And it's extending with, it's a cloud that extends far beyond, you know, the bounds of the galaxy. So it's not as densely packed. And one of the reasons why it might not be densely packed is related to the reason why it might be invisible, right? So it can't dissipate. So the reason these galaxies kind of start to come in, to spiral or collapse or things like that is they're able to dissipate some energy, right? Because of collisions and giving off light and heat, things like this. But if it doesn't really interact very strongly, it can't really collapse very well, and so it stays kind of more extensive. And that would kind of match the profile, so that seems like a pretty good theory. Oops. But wait, there's more, if that wasn't convincing enough, right? So one of the real classic proofs of the existence of dark matter came from gravitational lensing. So you might know from general relativity, or you've heard about general relativity, and one of the features of general relativity is that it bends light, right? Because space-time itself is warped by the presence of masses. And so that's just like light being bent by a lens, right? So the light will actually get from point A to point B faster through glass by going in not a straight line, right? And so that's the same thing with these cases. The quickest distance from point A to point B isn't a straight line as you go around a massive body, and so that means that the gravity itself can act like a lens. And so what you can have is like a very massive object, like a whole galaxy, right? And then you have a galaxy behind it, right? And then the light from that galaxy behind it gets bent around the galaxy in the foreground. And then when you look from the Earth, you kind of like extrapolate backward from the, what you're viewing, and you see some distorted picture of the galaxy behind it. And then you can do some analysis to double check to make sure this isn't just two galaxies, it's actually the same galaxy, but just kind of distorted. And thanks to computers nowadays, you can survey a lot of these and get an overall picture. But you can also look at some particular cases that are quite telling. So this is a pretty famous result from 2006 in observing something called the bullet clusters. These are galactic clusters. And they're able to use this gravitational lensing along with other measurements in like the optical, X-ray, infrared, and things like this. And they could show that the gas and matter and the ordinary matter in these galactic clusters. And so these were two galactic clusters that collided with one another. Now, because of the interactions, when these two galactic clusters ran into each other, they were inelastic, right? So all the ordinary matter, when it would come together, it would absorb some energy, and then it would give off bright X-rays and things like this. And so they can image that, and you can actually see one galactic cluster kind of going through the other. It's kind of like a bullet going through and splatting, right? But then there's if you can use gravitational lensing from galaxies and clusters beyond it to then image the mass density. And what you see is the mass density actually is separated from the matter density. So they think what happened was there's these two galactic clusters where the ordinary matter kind of was overlapping with the centers of mass of the ordinary matter and the centers of mass of the dark matter kind of overlapped, but then they ran into each other and the ordinary matter splatted, but then the dark matter just passed through each other like a ghost, right? And they separated. Right? And they're like, this is a pretty clear effect that is really well explained by dark matter. Because one of the alternatives to the dark matter theory is like, maybe gravity is modified in some way, right? So it seems like these velocities are too fast on the outer edges of galactic clusters and galaxies. Maybe like we don't understand the law of gravity. That's been wrong before. Maybe it's wrong again. But this seems to fit more the model of like some particles out there that are not interacting with each other. And they've seen this in a few other cases as well of these kind of colliding galactic clusters, and it seems to also be consistent with this picture. But wait, there's more. So there's also the very famous cosmic microwave background radiation. So the CMB, this cosmic microwave background radiation, is the light that's left over from after the Big Bang, about 380,000 years after the Big Bang, when the universe cooled down enough that atoms could form. And before atoms formed, they were just free charged particles that interacted really strongly with all the light. So it's like very optically dense, right? Some photons come along, bam, they run into an electron. Okay, gets emitted, it runs into another electron. It can't get the light can't get very far. But then when it cools down, the atoms form, right? Then atoms do absorb light, right? But only at a few particular wavelengths, right? So there's plenty of atoms between you and me, but light's getting back and forth between us, no problem, right? So essentially, approximately, physicists, we don't like to be too exact. So approximately, basically, light and matter decoupled at this point when the atoms form. They basically don't interact that much anymore. And so then this is light that's left over from the Big Bang. So you can analyze it. And so it's actually like nearly perfectly a black body spectrum. So these are the fluctuations in that black body spectrum at a level of like a part in 10 to the 5, so a part in 100,000. So they're very tiny fluctuations. It took a while to get these out. But these are supposedly going to be the leftover quantum fluctuations actually from the Big Bang that kind of are imprinted on this light. So one of the features that you can analyze actually is these multipole moments of this CMB radiation. And the idea is this, right? So if you had like a dipole, right, that would represent like, okay, this side of the sky. So you can look all around the sky, 4 pi, let's say, angular resolution all around the sphere. And if like one half of your sphere is hotter than the other half of the sphere, that would be like a dipole moment in the radiation. But then, okay, you also break it up into quarters, right? And like that would be like quadrupole. And you could break it up into eighths, and that would be like octupole. And you could go higher and higher, break it up into higher resolution. And you can kind of tell by looking at it that there is kind of a typical scale of fluctuation, right? There's like about this size, about this size, about this. Like there's kind of the fluctuations are larger on that scale. It's kind of the scale of the fluctuations. So they measure that, and they can actually predict this from theory and model it. And you can see that at about 1 degree in the sky, that's kind of where you get your maximum level of fluctuations. And then you also have a few other different ripples in degrees, when you get out to higher multiple moments where you kind of got a peak in the fluctuations. So what does this represent? So some of these interactions represent the following, right? As this, these what are called baryon acoustic oscillations. So this is kind of cool. So ordinary matter, right, back when it was all charged and freely charged and the atoms hadn't formed yet, it's bouncy, right? The electrons are coming in towards each other, but like, well, you know, like charges repel, so then they bounce off, right? So it has this bounciness. But the dark matter, as we've seen from our other example, is not bouncy, it just passes right through each other. So you can model like how much of it is bouncy and how much of it is non-bouncy in these fluctuations, and it gives different predictions for these wiggles. Actually, I was talking to someone, and you know, they were pointing out that like there was a time, right, at which you know, when they were doing the measurements, they'd seen the first peak and they'd seen the second peak, but they hadn't seen this third peak yet. So this was a more recent result. And the dark matter people predicted, oh, there should be a third peak right here. And then, of course, the modified gravity people said, no peak, there's going to be no peak, right? So this is great. Okay, we got it. We're going to, there's a prediction for both theories, and we'll see which one is right. And then, oh, the third peak showed up. Ta-da! So, you know, but then, of course, you know, some theories never die. Right? So they tried to make a comeback. But, so that was pretty convincing. So the theory of dark matter did make a prediction that came to be correct. So that was a you know, good scientific method kind of thing that happened. Okay, so the CMB, so another thing that I should point out too is like all of these measurements, they all match with about the same percentage of dark matter. So the ratio of dark matter to ordinary matter is about 80% from all these different scenarios. It's consistent, right? So then that's also pretty convincing. You know, one way to think about this too is it's like the ripples in a pond, right? So if you like disturb something, so of course Big Bang was a big disturbance, right? And then like the ripples kind of expand out. So that's kind of, you know, they have a typical scale depending on when the ripple happened and how long it is propagated and what the properties of the medium are. So that's kind of an analogy to these. We're kind of getting a snapshot of those ripples. Those are those fluctuations. But wait, there's more! So there's also this question of how nuclei formed after the Big Bang. So this is Big Bang nucleosynthesis, right? So the abundance of the light elements produced after the Big Bang, it turns out that's very sensitive to the ratio of the baryons, the neutrons and protons, to the photons. And then you can also note that the universe is flat, so you have a good idea from cosmology of how much the matter density is. And if you look at the photon density to total matter density known from the CMB, and then the baryon density from Big Bang nucleosynthesis, you can see that, oh yeah, the baryon density has to be only 1/5 of the total matter density, right? So again, you get that 80% of it's not baryon. So it's all coming together. And then on top of that, wait, there's still more, right? Which is structure formation. So the idea is that in order for galaxies to form from gravitational collapse, there has to be some local overdensity matter, right? So you can imagine the case where, okay, matter's all evenly distributed, right? So symmetrically, well, where's the galaxy going to form, right? You know, it's being equally pulled by gravity in all different directions. So you need some local overdensity. Now it turns out you can see what the local overdensities are for baryons from the CMB, from the cosmic microwave background radiation. And it turns out that those fluctuations we see in the CMB are 100 times too small to have had galaxies formed by today. So you need 100 times bigger fluctuations than what we observe in the CMB in order to have galaxies formed. And this is why not only do you need dark matter, but you also need cold, non-relativistic dark matter. So that they have these, they needed to be clumping up and forming big fluctuations long before when the atoms were formed at the point of the CMB. So, right, and so you need those big fluctuations, that's what seeds the galaxy formation. And some theorists say this is the most convincing evidence of all those things we said for the existence of dark matter, because they're like, this is like totally unsolvable. I mean, that's their opinion, I don't know. I'm just parroting what I heard somebody say, you know, because they're like, wow, this is just unsolvable without having big fluctuations or something else. Okay, so maybe I've given you, time has flown, but so maybe I pitched you on the idea that, hey, there's this stuff out there, this dark matter. But the fun thing is, if you're an experimentalist or a theorist or anybody, right, is like, okay, but what is dark matter? Nobody knows. It's like a free-for-all. We have no clue. People making up all sorts of wild ideas, and searching for them, and you know, we haven't found anything yet, so the search goes on, and so it's pretty good. So now I'll talk about this hypothesis. Maybe it's made of ultralight bosons, right? And of course, you know, everybody's asking, what is dark matter? Where is dark matter? But how is dark matter? You doing okay, dark matter? Yeah. Oh, okay. Now I have a shameless advertisement, but don't worry, the price is right. So it turns out we just came out with this open access free book. So totally free. You just go to the website, just download the PDF. It's all yours. Now, if you want a print copy, you have to pay a few bucks. But anyways, but it's just for free, and it you know, has that everything I just told you about why there's dark matter. It's all in there. That's where I got it from, and you know, other stuff and the things that are going on. So,
Wait,
yeah.
What level is that at? I mean, so just for students, you know, it's like, I mean, is it just for gray-beard professors?
No, perfect question, Doug. Thank you for asking. Yes. So, okay, my intention was what we tried to do when we wrote it. We tried to make it for, you know, a person that's finished undergraduate and knows their undergraduate physics pretty well, and you're like, hey, I'm kind of interested in this dark matter stuff. What's it all about? And then you should hopefully be able to pick this up and at least get a hint or a good picture of what it is. So that was what we're aiming for. You know, it's you know, different authors of different chapters. It doesn't always hit at that level, but I tried my best to, you know, at least I tried so I could understand it, and I figure like I'm more or less an advanced undergraduate, so I figured like, you know, it's pretty close. Right, so that was my intention. So maybe a first-year grad student who wants to, you know, figure out more about this field and see how it relates. So yeah, so hopefully pretty accessible, at least most of the chapters, I hope. But if it's not, you know, just call me up and I'll try to explain it better. Okay, right, so one of the popular hypotheses was it was made of little particles, so pretty massive particles, like particles with like masses of like 100 GeV, or 1 GeV, or 10 GeV, or something like this, right? That was the idea, and these were called weakly interacting massive particles because the idea was, oh, maybe they interact with ordinary matter through the weak interaction, the exchange of Z bosons and W bosons, things like that. But we've been searching. This is a good idea, very good idea. And you know, there's some cool theories like supersymmetry that predicted the existence of these things. Very hot topic. But they've been looking for these for decades and decades, and they haven't found anything yet. And in fact, you know, as we were talking about, like, you know, the WIMP community might have like blown their credibility a little bit because they're like, oh, for sure, it's around the corner, just around the corner. We have this firm prediction from supersymmetry. It's going to be right there. They looked at, oh, it's not there. Wait, oh, just around this corner. Okay, we made a mistake. It's right on this corner. And then, you know, this went on and on and on. You know, they're still not finding it. And now they're running up against some other technical problems. I don't know. So it's rough. So at least it's worthwhile to try to look for other stuff. So, right, so like I was saying, like maybe it's these super ultralight bosons that have so the funny thing about these ultralight bosons is very long Compton wavelengths and de Broglie wavelengths, right? So it's, you know, so normally you think of like quantum phenomena, that's like on the very tiny scale. But when you have such a light particle, the quantum wave-like phenomena is happening over, you know, macroscopic scales or even bigger. So the wave functions of these kind of particles are like big compared, in some cases, like big compared to the Earth, big compared to the solar system, right? So then, so that's pretty cool to think about. Like, so, you know, this, you know, being quantum mechanical isn't, you know, necessarily about being small. It's about, you know, your coherence properties, things like this, and like sometimes, yeah, so these particles have those properties but over huge distances. That's kind of interesting. Now, another thing is that they're really, really light. What that means is, you know, in order to be the mass, to explain the mass of all this dark matter, you got to pack like a ton of these particles into every, you know, unit volume so much that there's a really, really high mode density. So this is much like, kind of like laser light or it's, I mean, or at least like a bright light. It's not really coherent like in the same way that lasers, but it's you know, it'd be like very bright light where there's lots and lots of photons, in the case of light, per mode, right? And so then it really starts to act wave-like, like a coherent signal. So it's kind of very similar like radio waves or things like this. So then if you look for it, it's not really, don't really want to build a particle detector. You want to build more like a radio antenna or something, you know, to get to interact with the dark matter. So it's kind of a whole different ballgame of experiment. So one of the things that's kind of interesting, like if you think, oh, it's just a cloud of these wavy particles interacting with one another, well, they all have random velocities, and they all have random phases and things like that. So then it's going to end up being actually kind of like chaotic thermal light, like just like the light generated from a fluorescent tube, right? Like different atoms are bouncing around, generating different wavelengths of light. And it's coherent, but only, what did I do? Escape. Okay. Oh, I'm back. Press the wrong button. Right, so it's coherent, but over short times, right? But over longer times, there's these fluctuations. That's something else you can measure with photons. So that's kind of an interesting property, and maybe that's something, so it has certain coherence times, and you can calculate what those coherence times should be because all of the dark matter has to be trapped in the gravitational potential of the galaxy, right? So you can kind of estimate, like, okay, what's the spread in velocities, and that gives you a spread in frequencies, basically from the Doppler effect. Okay, so where do these things come from in theory? Well, one of people's favorite ultralight bosons that they think about is this boson called the axion. So I don't think, given the time, I don't go into too much detail here, but it comes out of symmetry breaking. So this, maybe you've seen a kind of picture like this of this kind of sombrero potential, and this is the same kind of physics that describes the Higgs boson. Now, the Higgs boson has to do with kind of excitations of this kind of radial component, but these axions are excitations of the kind of around the circle of the hat. So it turns out that, how hard it is to excite this in quantum field theory or something also tells you something about its mass. And so since it's very easy to kind of roll around the sombrero rim here, it means it's very low mass is the idea. Okay, but you know what? Given the amount of time, let's get to it and talk. Well, we can go back to this if people have questions, but I'm just going to speed ahead. Okay, well, I'll make one last final point. Is it turns out that these axions, right? So they get there. It's a cool way to look at very high energy physics in a really backwards kind of way, because the symmetry breaking that happens, the higher the energy scale that it happens at, that leads to, in the theory, a smaller mass, right? So it turns out that, basically your mass of this particle is inversely proportional to the energy at which the symmetry is broken. And so if you look at kind of the energy scales associated with different masses is, the scale at which grand unified theories come into play, where it's trying to unify the forces of nature, and there needs to be some new physics introduced to make that happen. That's at this scale of about 10 to the 16 GeV. And the Planck scale, where quantum gravity effects either become important or some other physics comes into play to explain it, so that's at 10 to the 19 GeV. And it turns out if you put those in the denominator to get the masses of the particles, those are kind of the cases that our experiments are kind of investigating, which is kind of cool because, we're, in a certain sense, we can say, oh, with some tabletop kind of experiments, we're investigating physics that's happening at these super high energy scales that, like, even if they gave us all the money we wanted, we still couldn't build a collider that would produce these kind of energies, right? So there's a cool way to kind of, from the back door, access this kind of physics, right? And a lot of the other experiments in the field, or at least that have been in the field for a long time, they're targeting higher mass axions that are accessing kind of lower energy scales. So that's kind of an interesting feature. Okay, well, let's talk about the experiments. Hey, this dark matter isn't going to detect itself. So, okay, so how can you detect it? Well, so we have these ultralight bosons, and the idea is, again, like we said, it's some kind of like wavy field kind of filling all the volume of space that we're sitting around in. And it turns out that they can couple this wavelike dark matter can couple in different ways to our standard model particle field. So you can get a coupling with photons. You can actually exert torques on spins. It can exert some new forces, or it could cause like what looked like constants of nature, like the fine structure constant. It could kind of modify the properties of the interactions of the standard model to make it look like those constants are varying, but it's really through the interaction with dark matter. So then what you can do is you can use all sorts of different precision sensors that are sensitive to these kind of effects, and then use those as an experimental platform to look for the dark matter, right? So, for example, for the photon coupling, you can use various electromagnetic resonators. For the so LC circuits and cavities and Fabry-Perot resonators. For torques on spins, you can use nuclear magnetic resonance, NMR, or electron spin resonance, ESR, and magnetometers, like what I'm, did a lot of my studies on. And for forces, you can use interferometers or resonant masses to see the forces, like atom interferometers, torsion balances, things like this. And for variation of constants, you got, if those constants vary, it's going to change the properties of atomic clocks, or you can do spectroscopy. So this is fun. So like the ultralight bosons can cause, in principle, all these different kinds of effects. And so that everybody that has their favorite sensor, they can just plug it in and try to look for certain types of dark matter. So just like I said, it's a total free-for-all. So pretty fun times. Okay, so so you can have couplings of the axions to photons, and that's what we look for in our SNIPE Hunt experiment. You can have couplings of the axions to gluons, actually, and that's actually going to induce electric dipole moments of nuclei, and so that's what we look for in the CASPEr experiment. And you can also get couplings directly of the axions to leptons, and that leads to coupling to the fermion spins, and that's what we look for with our magnetometers in GNOME, and we also kind of have an overlapping experiment with CASPEr. Okay, but first, let me tell you about SNIPE Hunt, right? So, I don't know, does everybody know the background of this? So the SNIPE Hunt, do you know what a SNIPE Hunt is? Do people know what a SNIPE Hunt is?
Yeah, so the older people in the crowd probably know. But yeah, so explain.
All right. Well, so when I was a kid, I was really into Boy Scouts, right? So we go camping all the time. Now, what do you do when the new Scouts join the troop? Well, the first thing you do is like, oh, guess what we're doing this weekend on camping? Oh, what are we doing? Oh, we're gonna send you on a snipe hunt. A snipe hunt? What's that? Well, there's these little animals out in the field called snipes, and they make these funny noises, wee, wee, wee. And you can only see them at night, so you get your flashlight, so everybody's good, you get a flashlight, you get a pillowcase, and you go out in the woods and go find the snipes. And then the little kids, the little tenderfeet scout go out there looking for snipes, and then all the older scouts sit back, ha 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 ha, there's no such thing as snipes, ha ha. Anyway, so there you go, that's it. Which I thought is perfect, because we're going out, so it turns out we're going to go out into the woods, go camping, looking for dark matter, which probably doesn't exist. It's just, so it's kind of an ironic joke on ourselves. Okay, so what's the idea? So it turns out, our idea here is that it turns out that the Earth itself could act kind of as a transducer to turn the dark matter into a magnetic field that you might be able to measure, which of course is right up my alley because that's what I know how to do, is measure magnetic fields. When you have a hammer, everything looks like a hammer, right? Or if it doesn't look like a nail, just hammer it enough, it starts to look like a nail, and then you can. So what we have actually is we have this Earth ionosphere system, so that can kind of act as a cavity. So people put their experiments in shields, but the Earth itself is kind of a shield, right? Because the ionosphere is conducting, and if you go deep down inside the Earth, not even that deep, but a little bit deeper than the crust, it's a very, very good conductor, right? So then in this kind of atmosphere gap between the ionosphere and a little bit under the surface of the Earth, you've got an air gap in between two shields. So this idea was like, oh yeah, can we do this? And then I got in contact with a friend from Stanford, actually Peter Graham, and he had a postdoc and a graduate student that started looking into it, and they went to town and developed all the theory, and then Ariel Arza got involved. So we wrote up a few papers on analyzing this possibility. Okay, so in particular for axions, what's the effect of it? So the effect of the coupling between the axions and the photons can be described just by modifying Maxwell's equations. Ah, nice, so there's some classic physics here. So what the axion dark matter does, it generates essentially an effective current along the magnetic field. So then if you look at this term in Maxwell's equations, the curl of B minus the time-dependent change of the electric field, you get this kind of equation describing on this side with this. So this Ga gamma is the coupling of axions to photons, the coupling string. So it turns out that on the surface of the Earth, effectively the electric field that we're sitting around in is pretty much zero. But the magnetic field, haha, is not 0. That's why our compasses work. So then that means that, you know, if you have a time derivative of the axion field, that's going to generate an oscillating magnetic field. Okay, so what we have then is, if you look at the ordinary Maxwell's equations, right? On this side you have the curl of B and the time derivative minus the time derivative of the electric field, and on the right-hand side, normally you have the current. So this term right here acts as an effective current, and that's the way to kind of understand the experiment. So this effective current is going to be the coupling of the axions to photons. The axion field gets, because it's the time derivative, it brings out a mass term, and then you've got the magnetic field of the Earth. So that's going to be generating current. So the Earth and the ionosphere set the boundary conditions that, you know, in the conducting place in between it, the electric field is 0. So then it turns out that this term here, right, because the electric field is 0 inside the Earth and 0 outside the Earth if it's a long enough wavelength, then that term is 0. So then now we have, oh good, so now we have a well understood characterized system that if this dark matter has a long enough wavelength compared to the height of the atmosphere, you can calculate the curl of the magnetic field is going to be around this axion field that's parallel to the Earth's magnetic field. Ah, great. So then we can solve the math, and we get that we should see a magnetic field of about 1 nanogauss, an oscillating magnetic field of about 1 nanogauss, times this coupling constant between the axions and the photon. Now we don't know, we don't know if that dark matter is axion, so let's assume it is axions. And then we also don't know what the strength of this coupling constant is. That's a mystery too, so we'll go out and measure it. So what do we have? We have, it's actually going to be a global spatial pattern determined by the Earth's magnetic field of this, you know, axion-induced magnetic field. And it's very coherent, so because of the temporal coherence of this field, it's actually got a Q, you know, the number of oscillations before it has a stochastic fluctuation of about 1 million oscillations. So it has a very narrow feature. So we said, oh, hey, you know what? Other people have already done the experiment, so we can do, it's a pandemic, so let's do some armchair physics since we can't go out. And we just look at the data that already exists out there from the Supermag collaboration, which is a geophysics collaboration just to measure the Earth's magnetic field. So we can just take that data, mine it, and see what we get. And the results of the analysis showed that we didn't find any dark matter. There's some possible peaks here, but then we did some further analysis to kind of rule them out. So we found no dark matter, and at this level of sensitivity, so above the line, the dark matter is ruled out by the Supermag data. And this coupling constant actually is pretty strong. So CAST is the kind of leading axion search experiment coming out of CERN. The C is for CERN. This is the astrophysics limit, the most stringent limit coming out of the observation of supernova 1987A. Oh, we're not too far away. And we had a pretty good slope going here, but we were only able to get, because the Supermag data was only sampled at 1 hertz interval, so we only got up to about 10 to the minus 2 in Compton frequency. So the idea is, let's go push to higher frequencies and see if we can do even better. And that's where we decided to start our dedicated experiment at higher frequencies. So this is my buddy Jason and Ibrahim and my fellow Cal State East Bay professor Eric. We said, let's go camping and look for this dark matter. So our idea is we stumbled upon these induction coil magnetometers, which are, you know, an idea so simple it just might work. It's brilliant. So it's just a ferromagnetic core with a big solenoid around it, 50,000 turns, and it actually has pretty remarkable sensitivity, you know, reaching down to levels of, you know, this is a picotesla, so it's down to like tens of femtoteslas, which is really a remarkable sensitivity for a magnetometer, and much better than what we got in our previous case. So, but of course, it's very noisy if you measure magnetic fields, you know, here, you know, on campus. So our idea was great. This is a great excuse to go camping. All right, so last summer we went out, we cooked food, we hung out at Auburn State Recreation Area near the North Fork of the American River, and we had a computer and some solar panels that were taking some data with our magnetometer and timestamping with the GPS. And then all of our buddies, my buddy Ibrahim and Jason, they went out camping at the same time on the same weekend. We all collected data. Oh, how fun is that? It was pretty warm. We chilled in the river. All right. So this is where we went. So we went here, and Ibrahim works at Bucknell University, so he's in Pennsylvania, and my buddy Jason, he works at Oberlin in Ohio, so they went to some other parks and went camping too. All right, so what did we do? So this was the summary of our data, this is how much the magnetometers were on, and we had pretty good coverage for about a couple days, but then something happened here in the middle that made our data look weird, and I'll show you a picture later. There was actually a magnetic storm. So there was a solar flare that then probably, and we knew it was coming because when I showed up at the campsite, my buddy Eric, who drove up too, he says, "Hey, great weekend to pick for this experiment. There's going to be a gigantic magnetic storm." And I was like, "Oh, yeah." I was like, I missed that. It was like on CNN, like, magnetic storm coming this weekend. And I was like, "Oh, dang, well, that's cool." But then I forgot about it. And then when we were analyzing the data, like, whoa, something really crazy happened in the middle. I was like, oh yeah, there was, and you looked it back up, and then other people saw it too. And so our data was kind of like, we saw something real there, but it kind of messed up our other data. So we split it into two parts and looked for the dark matter in this section and this section. Okay, so this was the noise level of our data here for our Hayward team and the Lewisburg team and the Oberlin team. And so it turns out there's some, our simple model in the experiment of the ionosphere isn't quite good enough to kind of reliably convert the signal or to interpret the signal in terms of dark matter above about 5 hertz, so we kind of cut off the analysis there. And then we have supermag data at lower frequencies up to a second we're still analyzing. So we said, okay, we'll just focus right for now on this 1 to 5 hertz region. So we searched the data, and so what we did was we were able to do a kind of a Bayesian statistics analysis, and this is the p-value, the probability that at all these different frequencies the data is consistent with noise rather than consistent with a dark matter signal. And then this would be the threshold taking into account the look elsewhere effect, because if you're trying to do something rare, like, okay, I'm going to try to shoot a basket into this little tiny basketball. If I shoot enough times, 1 million times I'll hit one, right? Even so, the rare event happens if you just try enough, right? And it turns out, like here, I think we have like 380,000 frequencies or something like that. So there's the chance of getting a rare event is actually not that bad. So this is the threshold, the 95% confidence level that if it crosses this level, it's not likely to be noise. But nothing actually crossed that. So this is kind of the histogram of that data. So that made our analysis pretty easy because we saw nothing. And it was quite Gaussian and everything was nice. So then we were able to set these limits, on the coupling of if we assume the axions are the dark matter, then this is kind of an upper limit on how strongly it could couple, which is not bad, not bad. All right, now does this seminar end right now, or? You could, but okay. Well, I'll just mention.
We started a bit late too.
All right. Well, I'll just mention a couple other experiments real quick. Okay. So the CASPEr experiment. So this is a collaboration between Boston University, Cal State East Bay, Berkeley, and Gutenberg University, and some theorists at Stanford and Johns Hopkins. So the idea here is pretty closely related, right? Maybe we'll focus just on this one in particular. So if there's a coupling to gluons, then this same axion field causes an oscillating electric dipole moment. And because you have a torque of D cross E torque, if you have an electric field and electric dipole moment, that'll create a torque. And these induced electric dipole moments are going to be parallel to the spin. But because of the oscillating axion field, it's going to be oscillating. So then you get an oscillating torque. Now, an oscillating torque, that's just the same thing you get in a NMR experiment, but there it's the magnetic field that you're oscillating instead of the magnetic moment's not oscillating, the magnetic moment is constant. So there's a kind of a one-to-one analogy with the experimental techniques you use for NMR and those that you use to detect this dark matter experiment. So the idea goes like this. So we polarize a bunch of spins, we apply an electric field perpendicular to the polarized spins, and then if it induces an oscillating electric field, it'll cause our sample to start to precess, just like it was driven by a magnetic resonance signal. And then we have a magnetometer, like a superconducting quantum interference device magnetometer, to read out the precessing spins. And so then in the frequency spectrum, you'd see a peak as you kind of scan through the resonant frequency. When you hit that resonant frequency, just like in NMR, you'll get the spins to spiral out, and you'll get a non-zero signal. You pick up a signal. And so this should give you some resonant enhancement of your signal, and that's what we're going for in this experiment. Now, we have to pick a sample to which we can apply an electric field, in this case, to get this D cross E torque. And so the sample we chose to work with is a pretty cool kind of thing, which is, it turns out in some crystals, you can have something called a ferroelectric. Ooh, I went backwards, sorry. Yeah, a ferroelectric, so it's like a ferromagnetic, but in this case, you polarize it electrically, and it stays electrically polarized. And so then at the position of the nucleus, if you have a heavy nucleus, then you have relativistic effects. So normally you think, oh, well, all the charges will position themselves so the forces cancel. And that's true. But if the nucleus is big enough, right, it's canceled on average, but it's not completely canceled everywhere because it has some finite spatial extent. So this is known as the shift moment. So you need a little theory background to figure out exactly what a good sample is. But this works quite well, and we could polarize it so it has this hysteresis curve. So you put an electric field on your sample, and then you ramp it down, and you still have the electrical polarization of the ferroelectric crystal. And then, so this was carried out in Boston. So then they dunk it in into a superconducting magnet, and they have liquid helium and in there. It's pretty awesome, and they get a pickup coil, and then they just do NMR on this thing, see if anything tickles it. Okay, this is the sensor, while they were out visiting and doing the experiment. And then once again, so they scanned through to look for any signals, and they got a Gaussian, in the log scale here, Gaussian distributed noise, but nothing. So these were the signals. So you're looking for some outlying signal that they have some large amplitude signal, and these were all. So these were the kind of standard signals, but then we rescanned again, and we didn't get resonances in the same places. So this turned out to be noise. So then you're able to set some limits again on the coupling of the axions to these nuclear electric dipole moments, and you're scanning this space. So we're hoping, to sort of kind of demonstrating the principle of how the experiment works. And we're getting pretty close to some limits from astrophysics, but we're hoping to extend it down here with bigger samples, colder temperatures, and kind of get down to search for something called the QCD axion, which is everybody's like super favorite axion, but we've got a long ways to go there. Okay, so maybe with one more minute, I'll just mention GNOME, our other experiment collaboration. So this is pretty cool. So the last two experiments we talked about, this is like we're just bathed in dark matter all the time, and it's like coming through, and we just set up, and but what if we're missing it? What if the dark matter has somehow clumped up, right, into like, small on the scale of the galaxy, but big maybe on the scale of the Earth, into little clumps? It's not like totally implausible. So maybe it's like interacting with itself, but not with a standard model particle somehow. And then, you turn on your experiment and you see nothing. And then every once in a while, a big clump of dark matter passes through, and you go, blue, there's a big spike. But then you're like, oh, what the heck was that? It's probably nothing, let's just keep averaging, right? You can't really, that's not the hypothesis we're testing, so you kind of miss it. So, but what if it was real, right? And we kind of threw the baby out with the bathwater. Well, so the idea was, okay, let's make a network and see if we all see the same thing at the same time in the right pattern. Oh, maybe that could be a way to search for it. So the idea is to make a global array of sensors. And so we proposed this idea, and then talked to a bunch of friends, and they're like, yeah, let's do it. Why not? And so it happened. So the idea is like some weird dark matter comes through once in a while, and then causes some little blips. And then it should come in a certain particular timing pattern and amplitude pattern if it really is a real dark matter signal. Otherwise, it would be inconsistent with the noise. So that's the idea. So we actually formed a collaboration. We've got sensors in the US, in Europe, in China, in Australia, even and Israel. So you know, people got a little hyped and got involved, so that was cool. We started having meetings. First we met in Northwestern, then we went to Germany, then we went to Poland, then we went back to Germany again, then we went back to Germany again. so having a lot of fun getting together talking about dark matter. Okay, we'll just skip ahead. So this was actually the kind of magnetometer that I built as a graduate student, and then we built in our lab at Cal State East Bay. So it just has, we have some lasers, right? So one laser polarizes the spins, and, no, sorry, this laser, sorry. This laser polarizes the spins, and this laser reads out what the spins are doing, and we're looking for any sort of torques on the spins due to the dark matter. Right, so we have a rubidium vapor here in the center. We have a shielding, so this is the shielding that the Earth acts like in the SNIPE Hunt, but here we apply our own shielding. We have our laser beams. We have a polarimeter read out what the laser is doing and some detection electronics. We stamp it with GPS so we can get the timing right. And then we flag it in case there's any like wacky things that somebody kicks a table in the lab so we can rule that out. So this is like detect glitches. We got that from LIGO. Which also, this whole idea was kind of inspired by LIGO. Like, oh cool, you can measure things in places and then by these transient events, like yeah, we should do the same thing. So this is our setup in at Cal State East Bay. So you can see it's just a lot of optics, some lasers, a bunch of electronics, and reading out things in the data. So we actually have taken 5 science runs with varying levels of success, where this is our sensitivity. So science run 2 was pretty good. We got pretty good, like, down to about a picotesla in sensitivity. And science run 5 was even better. We got below a picotesla in sensitivity. We had some spotty coverage here, and usually it has to do with, you know, how many stations are on all at a given time, you know, and how long you can keep everybody. You can keep all the cats herded together to take data at the same time, which isn't always easy. You know, and an important thing in any of these experiments is to make sure your experiment is actually turned on. You know, sometimes, you know, hey, is it working? You know, you gotta, I mean, if you're measuring 0 all the time, that could be because there's no dark matter, or it could be because the thing's not working, so you gotta check. So we made sure every hour on the hour we did a pulse at different frequencies so we could get a bandwidth of our, and basically a response curve of all of our sensors. So that was a way to check ourselves to make sure we weren't spitting out garbage. And look, sometimes we were. So like, here's our Korean station, and sometimes it just got 0 everywhere. Like, okay, we got to throw that data out. That was not working. And then you can see sometimes, you know, for example, in Lewisburg, they're having pretty big fluctuations of the amplitude, so it has to be like renormalized and corrected. Something weird is happening there. Oh, but good old minds look so steady. Very nice. So, right, so the idea is like, what are we looking for? Well, we're looking for things like this. Like, okay, maybe the dark matter is in like the form of giant bubbles. So like a bubble comes passing through, and you just see the dark matter. It's all in the wall of the bubble. So the bubble comes through, and you just get a little pulse, right? So that's that idea. So, right, and then, but of course, different stations are pointing in different directions, and they're in different locations. So then you get different sized pulses and different timing of pulses everywhere. And so then you have to, then our data analysis kind of looks, it's kind of like pattern recognition. So you're looking for pattern recognition to see if it matches a bubble going through or if it's just random noise. So the data analysis is kind of cool. It kind of works. So like you can inject a signal like LIGO does, right, into the system. And if you just do it at all random times and you scan through using our analysis, you know, nothing really shows up if you kind of do a scan of the sky. But if you do the timing consistent with a wall passing, or the Earth passing through a wall, you get kind of these curves, and they all kind of intersect at a point. So it kind of identifies, bing, like something stands out of the background. So that's how we do the analysis. But alas, we searched and we didn't find anything. But once again, we can rule out this model of dark matter to some extent. And like the previous laboratory searches that constrained this kind of thing actually were done by Norman Ramsey, the father of the atomic clock, back in 1979. So it'd been a while since this kind of thing had been tested, because we're getting pretty far out on the fringe of what's done. But hey, you know, some legit people thought about it back in the day. So we were able to constrain some of these interaction symmetry breaking scale and so on. All right. Yeah, but there's other crazy theories you can like check using the same kind of model. So maybe it's not a ball, maybe it's some kind of, maybe it's not a bubble, maybe it's kind of some kind of ball, and it looks like that would work. You'll kind of go through the ball, and then you'd see a signal. So depending on your model of the ball, you might see an oscillating signal that kind of is a pulsed oscillating signal, and then it's kind of like the axis changes as you move through this, the star, the big ball of axions. You'd see some kind of weird dependence. Could also be one of these cue balls, some other kind of ball of axions or scalar particles, which kind of has a different profile. It only gives you a peak at the edges, boink boink. It's kind of like two balls. It's more like a bubble, right? Or maybe, maybe crazy stuff happens when like black holes merge or neutron stars merge. There's a lot of energy given off. And like, I mean, yes, admittedly, a lot of it goes into gravitational waves, but what if a little bit went into something wild like axions or some other kind of weird boson? So, so maybe we could look for, weird exotic signals coming out of these big events. So that's something else we were looking at. So you have like some black hole emerging and it spits out a pulse of one of these weird fields, and that would propagate over to the Earth. And actually, if it has a non-zero mass, it'll undergo this frequency chirp. So we kind of look for that in our data. So we called these ELFs exotic low mass fields, so we could have GNOME looking at ELFs. That's all it is. Okay, so amazingly, that's the end of my talk. So yeah, so that's the kind of stuff we're doing. It's really fun, and getting a lot of people together in a collaboration, and building tabletop scale kind of sensors, but then investigating some cool physics that involves like particle physics and cosmology and astrophysics, and just having a blast. So anyway, well, thanks so much for your attention, and thank you very much.
Thanks for a great talk, Eric, and we have time for questions.
Hey, I was interested in your SNIPE Hunt and your locations for examining the magnetic field. I was wondering how directional your experiment was, and if you thought about maybe trying some funky latitudes and longitudes rather than.
Oh yeah, great question. Right. So so it depends on your dark matter model. So for the axion case, right? So we know in that case you have kind of a predictable dynamics, which is it's going to be a current along the direction of Earth's magnetic field. So then our main concern there, if you wanted to get away from the city, and we got lucky. I didn't even know what I was doing. I reserved the campsite too late because I had these campsites picked out, but then I waited until like final exams, and I tried to reserve them, and they're all already booked. So I scrambled, and I booked the only one that was left, and it was this Auburn State Recreation Area, which turns out that Auburn State Recreation Area was slated to be a reservoir at one point. And they even started building the dam to dam it off. But then they realized there's a fault line there, and that dam was going to, the next big one hits, is going to be a disaster. So then they stopped building the dam. But then the California legislature never gave back the land to not be a reservoir, so nobody can build there because it's going to be a reservoir. It's not going to be a reservoir. But legally, it's going to be a reservoir. So then there's actually no human-built, there's no electronics, which is why nobody camps there, because there's no services, right? It's you have to pour in your own water and everything. I was like, but it's great for the SNIPE Hunt because actually the magnetic noise is really quiet. Anyway, so that was the main concern there. So yeah, you kind of know the pattern, and it just depends on the Earth's magnetic field, and so you can kind of predict that and use it. Now with the alternative model I didn't really talk about too much is there's another model where there are these hidden photons. So they're like ordinary photons, but they're have a little bit of mass, and they don't interact with anything at all. So that was actually the original idea why the non-interacting particle kind of worked for the name, because they don't interact at all. But like neutrino mixing, what can happen is there's different basis states for the mass, for the propagation eigenstate, and then the interaction eigenstate, and so they get mixed. So just like you have neutrino oscillations, you can have hidden photon-photon oscillations, and so that's this mixing parameter that comes in. So, but those have polarization, like photons have polarizations, but it's random, right? It's just like, randomly polarized in different directions. So the spatial pattern is coherent over some coherence time, but then it'll just adjust. So then it's kind of hard to predict, like, any particular location that would be better than another particular direction. So, but the induced pattern, like if you have a network of magnetometers, there's a particular induced pattern. So like, in the case of the axions, you're sensitive to basically the curl of the field, so it's the circulating field around the Earth's magnetic field. So you kind of know, like, oh, if you orient it that way, that's going to maximize your signal, right? And yeah, so there's this global pattern. So that's what we use in the case of the supermagnetics. It's like 500 magnetometers or something like that. So that's too much to analyze. So you kind of reduce it, you project it all onto this kind of like global magnetic field pattern of the net group, and then extract it that way. Yeah, it's a super interesting question. Yeah, so it's you know, it's kind of fun to, you know, look through all this, and it's you know, there's Maxwell's equations that basically describe this as like, oh, you know, if you really have understood your classical E&M, you can actually kind of work it out, and it's kind of fun. So I don't know. Does that answer the question, kind of?
A little.
A little, yeah. So maybe there's a better, yeah. I mean, maybe there's a better idea of a way to optimize it, but that's what we thought of so far.
For the GNOME hunt, it seemed like you were assuming that the dark matter was going to be in a sheet, like
Yeah,
and
so
then later on you were like a ball. Now to me it seems like the ball would be like the more natural thing, right? If you have a
yes.
gravitating mass, it's going to basically go into a ball. But so why did you guys look at the sheet? I mean, is there a specific reason?
Well, okay, the story is, I mean, it's like many things in physics, it's a bit historical. So we first came up with the idea, like, oh, maybe we could look for crazy stuff with a network of magnetometers. But we're like, what crazy stuff? So then we went to our theorist friends, like, hey, you know any crazy stuff we could look for? Like, no. You know any crazy stuff we could look for? No. But finally, one friend, Maxime Postella, was like, oh, I know something you could look for. And so he came up with this idea of these domain walls, actually. So kind of like ferromagnetic domains. And so the concept is, like in the early universe, actually it goes back to the spontaneous symmetry breaking thing. So you could have this axion field, like this, undergo this spontaneous symmetry breaking, but it could have different values. So the thing with the spontaneous symmetry breaking is that even in a region where there's no axions, it can have a non-zero vacuum expectation value. This is this idea. And then it could be different in different places because it didn't all happen in the same way at the same time. And then at the boundaries, you have to go from one vacuum value to another vacuum value, and then it creates this wall, this tension. Right? Now, in normal theory, these like unravel themselves in the early universe, and actually that's how the axions get produced in the first place. But Maxime had some idea where maybe they could be quasi-stable, and then they could be persistent. So it'd be like these little domains floating around. I'll just call this out, say. But then you talk to the theory community in general, like, maybe that's a bit of a stretch, and like to get them to survive is hard. I mean, the production is very, they're like, yeah, that definitely happens, but like, yeah, it should go away. Like, really. But then that's when other people are like, yeah, well maybe, and this other the ball idea came up. And then, like the cue ball idea is like pretty good, like pretty solid, like theoretical idea in the sense that like it makes some sense, and it's like it's pretty stable. And the idea there is if you just throw in some symmetries, you can end up with these axions having a charge. So they can't be like created and produced and vanish like freely like a photon can be. So now that they're charged, so then there's this conserved charge, you can't get rid of them. But then they want to minimize kind of the energy in them, so they'll under the right conditions, and then they'll kind of form a ball. But then you can't get rid of them because they kind of go at the lowest energy state of the ball. And that's this idea. The Q is for like the charge of the axion.
So it's an electric charge? Or
no, it's like a new made-up charge, like
okay.
a magic poofle charge or something. I don't know. Yes.
Do you know anything about from the astrophysics about the density of this axion, or any other?
Oh, yeah, good question.
You showed the picture of the velocity, so you can infer some density of this.
Yeah, absolutely. Yeah. So thanks to all the research on the dark matter, you can actually compute what the local dark matter density on average should be around at the position of the solar system, which is about 0.3 to 0.4 giga-electron volts per cubic centimeter. So that's like, so if you think of like a proton has about a mass of a GeV, so it'd be about a half a proton per cubic centimeter is the average density of the dark matter. So the local density in the solar system is pretty low. That's like a pretty low density. But then if you sum it up over the whole galaxy and out to the edges, then it starts to add up. So it's like that in every little square
Is it
cubic centimeters.
the same everywhere in the universe, or is it fluctuating?
Oh, so that's particular to, yeah, so the density does vary as a function of how far you are away from the center of the galaxy. So that's, yeah, so the idea is it's virialized, so there's going to be sort of this virialized kind of Maxwell-Boltzmann distribution of the dark matter all flattened out. So when you get out to our edge of the solar system, you know, that's about the density and the velocity that you get out from where we are. So you can kind of predict that. But there's all sorts of subtleties, right? Because this is assuming it's all well virialized, but then people also know that the Milky Way has like swallowed some other galaxies recently, and those aren't virialized yet. So there's these streams of stars, and they're like, oh, there could be like streams of dark matter that are like, so yeah. So there's a lot of uncertainty about it too. To be honest.
And in between galaxies there's none, so basically they're clumped in the center.
That seems to be the case as far as I understand it. It's like the idea, like the present idea of structure formation is that it's the dark matter clumps first, and then the ordinary matter falls into the gravitational potential of the dark matter. So then, generally speaking, where the dark matter is, that's where the matter is too. But yeah, but I don't know like the observational evidence like for the presence of dark matter where there isn't matter. I mean, I guess you could look for it with gravitational lensing. I guess they do look for that kind of thing with gravitational lensing, but I don't know what the state of the art is. But that's the general idea. Yeah, it should all be overlapping pretty much.
Okay, so any other questions, comments? All right, well, if not, let's thank Dr. Kimball again.
Thank you.